Okay, those on Zoom, you didn't miss anything. Okay, so currently the LIGO Virgo Cagra collaboration has seen on the order of 100 merger events, and in the O4, which is coming out, it's going to be a few hundred to 1,000 events that they're expected to have seen. If you have ever looked at actually I think this is true, but don't quote me on it. The first gravitational wave signal they ever saw, I think it's still the loudest gravitational wave signal they ever saw. And typically gravitational wave signals are extremely weak because of course it's couples only gravitationally, and there's a lot of noise sources around you. So gravitational wave signals are usually completely dominated by noise. So what LIGO does is it uses a match filtering method to detect it. And that basically means that if you know what your signal looks like, then you can just take what you measured, take what you expect the signal to look like, just dot product, effectively just dot product them. And then you can, and if you get if you get a large number, then that signal is present. If you get a small number, then that particular template that you choose to compare it to is absent. The problem with this is, I'll get to it in a second, is that you need a huge amount of templates to do this comparison problem. So it's very time consuming. And here instead of doing anything like match filtering for me to tell what exactly is the gravitational wave template I'm comparing to, I'm going to focus on a simpler task, which is just to say whether there's in this data that I gave you, is there a gravitational wave signal present or not, without saying anything about what type of black hole merger it came from, what are the spins of the black holes, any of that stuff. The reason I chose to do this work is because I wanted to learn about neural nets, and it's really hard to find data about anything. For experiment, this is easier because they work on experiment. But it's really hard to find reliable data to actually do something. But there happened to be a Kaggle competition, and for those of you who don't know, Kaggle is like this website where they post problems, and machine learning experts from all over the world come and solve that problem. And I'll just tell you, I did not win the competition at all, and not even close. But I think I found I tried to solve a slightly tangential problem, which I'll describe. But I also benchmarked my results to what, so quote unquote, sort of the close to the best results were in the competition. And I'll show you that I do not perform as well as them, but not by much. So I'm pretty close. Okay, so yeah, so I was motivated by this competition, and actually I joined pretty late, and by the time I learned about neural networks and all, it was over. And if you look at my rank, I just submitted some random. I just first tried out some random ways to say it, and I'm like 2,000th rank or something like that. But I can't do anything after the competition is done. So I couldn't do a true apples to apples comparison with other people once this work was done. Okay. So the gravitational wave signals depend on several parameters. The parameters being the mass of the two black holes that we're considering merging, or even two neutron stars, or a black hole and a neutron star. Its inclination, like where is it in the sky? Its distance from us, the spins of the black holes, and so on and so forth. Gravitational wave signals that we try to see in LIGO will have characteristic frequencies from 10 to 1,000 hertz. So what happens is when two black holes start to merge with each other, they start out with really slow frequencies. They emit gravitational waves. They become closer and closer, and as they become closer and closer, they rotate around each other faster and faster until they merge and form a single black hole. So each gravitational wave, each merger, no matter what it is, will have this form where it starts out with a low frequency, goes to a high frequency, and this is close to where the merger happens. But this is a time series this is only showing the last 2 seconds right before the merger. And on the y-axis, what I've plotted is the gravitational strain, how much your space is getting stretched by, on Earth. But of course, we don't see this. What we see is something more like this. where my data is completely dominated by noise. So if I just look by eye, I won't be like it's completely dominated by low frequency noise. So if I look by eye, I don't see any presence of gravitational wave signal. And in fact, if I look at what the noise sources are and plot what's called the power spectral density, which just tells you which Fourier components are present in what magnitude. The noise is dominated by completely by low energy noise. I think this seismic noise is mostly responsible for this. And then, at higher frequencies, you have like some other line sources, maybe like power lines or something else. I'm not exactly sure what these line sources are, but this is how the power spectral density looks like. The first thing that you do when you analyze data like this is you try to whiten it. And by that, I mean that you want to remove, you want this power spectral density to be flat. And I don't know why, but it's empirically true that it gives better results. So what you do is you take your time series, you Fourier transform it, and then you divide by the average of the noise only power spectral density. So this power spectral density is taken from noise only templates, which I'll describe in a second. So you divide that Fourier transform by the power spectral density, and what you end up getting is just Gaussian white noise once you do that. And actually that kind of helps. So the signal that I showed you before, if I perform the whitening procedure, then you'll see that this high frequency part now started showing up after I did this whitening procedure. So now I can tell by eye, but this is still an extremely loud signal. In most of the signals that you'll see, you will not see anything like this. You'll just see like something that looks like random white noise. This I'm just showing for illustration purposes. So the first step you do is you do this whitening procedure where you make sure that all the frequencies contribute equally to the noise and to the signal. Okay. Before I go ahead to describe eventually the neural network part, I'll need to describe something called the continuous wavelet transform. I think everybody here is familiar with the Fourier transform. And Fourier transform is used for when the signal is stationary. So if I want to know what frequencies are present in the signal, I would use a Fourier transform, and then it will tell me that, okay, these frequencies are present in this given signal. But if I want to know which frequencies are present at what times, because not like, think of like a piano playing, right? Not all notes are present at all times. It lasts for a certain amount of time, then you play the next note. So if I want to know what notes exist at what times, I do something called a complex wavelet transformation. So what I do is it's like a Fourier transformation, but it's multiplied by this wavelet. And you can choose, there's various choices that you can use for the wavelet. I won't be getting into that. But what you do is you take the wavelet and then you slide across. And then you go to a higher frequency. You make the wavelet smaller. You take it again, you slide across. And what it does, it tells you what frequencies, not only what frequencies are present, but what frequencies are present as a function of time. Okay. And this is what LIGO uses to visualize their data in a way. So you guys might be familiar with these chirp plots. And the reason they're called chirp plots is because just like, I guess, I can't recall right now how birds sound like, but if you apparently this looks like a chirp. So like as time progresses, you go like higher in frequency, right? And that's what this is showing. That as my time progresses, the black holes are spiraling faster and faster, and frequency of the gravitational waves increases. So this is known as the chirp plot, and hence the title of the talk. And I want to amplify the chirp. Okay, so yeah, so this is the basic data that I'm going to work with. I'm going to work with images instead of time series signals. I want to mention one thing, which in generating this, I have only kept the amplitude of the signal and thrown away the phase, which is very bad because there's a lot of information in the phase. And in my upcoming work, I'll include the phase information in what I'm doing as well. But for now, I'm only working with the amplitude of the CWB transform, not the amplitude and the phase part as well. Yeah.
What is G, the previous slide?
Oh, you mean what exact function it is? I think it's like it's like a decaying sinusoidal. I can look at the exact exact expression for you. Yeah.
So the function captures, the volume information.
So it tells you what frequencies are, so because it has a finite size in the time domain, right, because it decays as you go ahead, it tells you that, okay, this frequency is present at this point in time. Oh, by the way, there's an uncertainty principle associated with this. So when I choose, thank you for bringing this up. So when I choose my wavelet, I can either know which frequency, I can know what range of frequencies was present at what time, exact time. So I can know the time information really well, or I can know the frequency information really well. So in reality, the signal is not as broad. It's just that there's down here, I'm working with fatter wavelets. So it's hard to resolve in time where exactly the signal exists. So there's a little bit of uncertainty principle that exists in this transformation. Okay. I'm going to use two data sets in this talk. One is what I'm going to call the benchmark data set. That's what I'm going to use to benchmark the performance of my models against. And this came from the Kaggle competition, so I have no control over this data. So what this Kaggle competition consisted of was about 500,000 labeled signals for LIGO and Virgo, and each LIGO signal has two, because LIGO has two detectors, Hanford and Livingston. So it's total of 3 time series times 500,000. To avoid computational expenses, I used only 1/4 of this data because I was good enough to see how I was performing. The next thing is I'll drop the Virgo signal because, oh, by the way, this is simulated data as well. It's not like it's actual data from LIGO and Virgo, but it's data given by I guess something associated with the LIGO Virgo collaboration. So it is simulated data still. That's not the actual data. Only LIGO data I'm going to consider for this. So I'm only going to consider from this LIGO data from the Hanford and Livingston side. And the reason is that because LIGO, the two detectors are very similar to each other. They have similar noise profiles, whereas Virgo is just much more noisier. So we will ignore that. I use anytime I do anything, I take 90% of my data randomly for training, and 10% is used for validation, so that I don't end up overfitting. Okay. The second data set I use is a fake data set that I generated. And the reason I need to generate is because I want the network to learn how to clean a signal. Here is just noisy signals, right? It gave me 500,000 noisy signals. So I don't know what the underlying clean signal looks like. So I'll tell you of a way to use that still. But to take my first step, baby step, I wanted a noisy signal and a clean signal. So for that, I had to generate my own data set. And I did that by LIGO's library, which lets you do these things. So I chose a range of parameters for masses, spins, and all that. I hope that my data set here was like the parameters range I chose was comparable to the benchmark data set, but that's not a guarantee. I'm just guessing. And I generated 70,000 such signals. So that's the fake data, so the synthetic data set that I generated.
So,
yeah.
So here, what do you mean by signal? Signals, only gravitational wave signals, or even those?
You mean over here?
Yeah.
So it's measured. So out of this 560,000 points, 200, like half of them, 280,000 are time series signals with a gravitational wave present, and 280,000 of them are time series signals with no gravitational, just noise present. And they tell you which one is which, so you can train it and then try to generalize it to unseen data.
Yeah. So some of them contain signal, real signal, and some are not contain.
So yeah, some of them contain not real, it's still simulated. So simulated signal, and some of them contain no signal at all. Okay, so the task I want to do is I want to on the data that's unseen by my models, I want to predict if there is a gravitational wave signal in the top. So it's just a binary classification task. Yeah, my data as I was just mentioning is a noisy time series. So the pre-processing steps I follow before I begin any machine learning training is I take the time series, I whiten the time series, and then I make a CWT image out of it. And that's like the first step that I started. And like I mentioned, there's two different forms of data, the benchmark and the data set that provided by compression, the synthetic data set, which is generated by me.
And your, the signal template given, generated by you with some guidance on what it should look like, or just?
I was just taking a guess, like, that the black hole should be between 5 and 70 solar masses, and the spin should have a particular distribution between -1 and 1.
Because, LIGO give you any guidance on what the signal?
The compression didn't give me any guidance of how they simulated their data. So, I was just guessing. So it's possible that I don't completely overlap with the, with their data set. But there's no way for me to find out. Okay. Thank you. Okay, now before we say how we use LIGO data, let's just take a step back and discuss neural networks. So a neural network is just a construct to learn a complex nonlinear function. So here, what I'm showing is something called a fully connected neural network, where I can take, this is an image, but in reality, I can just unravel it and make it into an array, right? So I can strip this image, make it into an array, like the first pixel will go like this. Sorry, the first row will go like this, and the second row will like one after the other. I can just, if it's 28 by 28 image, I can make a 784 sized array out of it, and I can feed it. So if my classification task is to say, okay, is this a dog or a cat, the given image I provide, I can use a fully connected neural network to do that. Although that's not the best thing to do, you use what I'll describe next, which is a convolution neural network. And you can train this network to classify whether it's a cat and dog. And this network has three things. One, it has the input layer, which is just I'm feeding the image into it. The output layer, which I can label data set. So I take first data sets, I know which one is cat and dog. And that will tell me what output, whether it's one over here or one over here. That's the output text. Sorry?
You don't have a non-option?
I think if I were to train it on cat and dog, and if I just provided the image of a car, something like that, I think it will still try to predict it whether it looks like more like a cat or a dog. Yeah, there's no, I mean, yes, I could have built a none option as well. That's also possible.
No, what I'm saying is that you don't need to have a template for none. So the AI should, your machine should understand whether it's not something different.
Not unless, so the machine only, if I only feed it cats and dogs and nothing else, then in the machine's universe, only these are the only two classes that exist, right? So if I feed it a car, it will still try to propagate that information, and it won't be like 50-50 or something. Like I don't know which one it is. It will still prefer one over the other. So yeah. Yeah, so you have the input layers, then you have hidden layers, and to get from the input layers to the next layers, it's just a bunch of matrix multiplications, like I'll explain in the next slide. And I can have n number of hidden layers, and the more, so right now I've just shown one, but I can have second, third, fourth, fifth, and the more I have, the deeper my neural network gets, the better, the more complicated nonlinear function it's able to make. So any neural network training consists of two parts. One is called the forward propagation. Well, I don't know why I showed you in both cases. Sorry about that. One is called the forward propagation, where I start with the input, and I have made this matrices, which is theta ij. I multiply it, get the hidden layers. I have another set of matrix, theta jk, multiply it, get the output. Now I know that it's going to predict a probability for whether it's a cat or a dog, but I know in my training data whether it's a cat or a dog. So I define a loss function that tells me how close is my prediction to the actual answer. And if it's not close, then what happens is I do something called back propagate. So I say this is my loss function j. If I were to vary my parameter theta, then my prediction will match it better. So what I do is it's like a gradient descent. I just back propagate that information, correct my matrices theta, and that's how the neural network runs. And I do that over and over again, showing it multiple images until it converges in some sense. By the way, if these were just matrices, then a matrix multiplying an array, and it doesn't matter how many matrices I pull onto each other, the output will still only be a linear function of my input, right? Because it's just matrix multiplication. So but I want to be able to learn non-linear functions. And so instead of just multiplying by theta, I multiply the vector by this theta, this weights, what I call the weights. And then I apply something called an activation function to it. And this activation function is a nonlinear function. So it can be a sigmoid. So I take theta times x, and then I apply the sigmoid to it, or the hyperbolic tangent to it, or something called the ReLU, which we don't have to get into it, but yeah. It's just 0 if the input is negative, and x if the theta times x if the input is positive. So this introduces nonlinearity, which allows the network to learn more complicated functions. So this step is essential to put in different activation functions. All right. Now, what are convolutional networks? So previously, what I showed you was neural networks, which relied on the operation of matrix multiplication to propagate the information through the network. Convolutional neural networks are networks that rely on operations called convolutions. So if I have a cat, I can represent it by basically a n by n array, right? And what I can do is I can take a filter and convolve it, this pink thing, the kernel is called a filter, and I can convolve it with the image. And let's say I took some random filter, 1, 2, 3, 4, 5, 6, 7, 9. In reality, what my neural network is doing is learning these filters. But just an example, if I knew what my filter was, then I'll multiply it with this patch. I'll get 31. I'll move it once over, or however many times I want, whatever leap I want to take in the direction. I'll do it again, fill in the next square. I'll do it again, fill in the next square, and do that process. So that what I started out with an image, I ended up with I started out with an n by n array. I performed the convolutions. I ended it with a smaller array. So in reality, what happens, the way deep convolutional neural networks learn, is that in the earlier layers, they will learn edges. So they will learn to detect, they'll take an image and they'll learn to detect edges, like straight edges, horizontal edges, vertical edges, diagonal edges. And if you keep going deeper and deeper into the network by performing more and more convolutions, rather there's also intermediate operations called pooling, which is just a name for you take all the numbers in that square, and if you do max pooling, you just take the biggest number and just keep that in as you go ahead. But anyway, as you go deeper and deeper, if I were training a convolutional neural network to detect cat versus dog, well, the initial layers will just learn the edges of the image. The deeper layers will actually start constructing ears and eyes. So if you actually visualize these deeper layers, there will be some sort of eigenbasis to separate a cat and dog, right? So these deeper layers understand more higher level information of like, okay, it's a cat's eye, so it looks different than a dog's eye. And the network will learn to sort of create this, you can kind of interpret it as it's learning to separate these images by focusing on features or constructing features of cat and dog that I think would even be human understandable in this context. And then what you do at the end is you still have a stack of n by n, not n by n. You started out with n by n, but a smaller stack of matrices. Now you unravel them, make it into an array, and then you put it through a fully connected neural network, like I showed you before. And then you classify whether whether it's a cat, dog. In this image, it's a Donald, Goofy, or Tweety. And that's how a convolutional neural network works. What I want to do is a type of convolutional neural network. It's called a UNet. I'll tell you why it's called a UNet in a second. So in the convolutional neural network, I have a cat. I feed it through a convolutional neural network. It performs its convolutions. It goes deeper and deeper, and I predict whether it's a cat or a dog. But I don't want to just get a single number as the output, right? I want to start out with a noisy signal and get a clean signal. So I want to map it back to the same space that I came from. So I need convolutions which learn more and more features as it goes deeper. And I need inverse convolutions to sort of reconstruct the image back, to learn how to reconstruct the image back from the feature stuff. And so for that, I need something called transpose convolutions, which They work exactly like convolutions, so we don't need, we don't have to go into details how they work. But this is the type of architecture I want. This is the type of convolution network I want. So some people introduced then, like a few years ago, I guess maybe 10 years or more ago, people introduced the concept of UNets, and it was first introduced as a medical segmentation neural network. So when you see an X-ray or MRI or something, you want to know where the tumor is. So what you do is you use this unit, and the way this unit works is it's also used in self-driving applications, because when I'm driving, I want to separate which this part is the car, these pixels are the car, this pixel is the road, and so on and so forth. Right? So in a way, what it's doing is actually filtering information. It's telling me which part of the image is what, and then I can decide what to keep and what to throw based on my choice. So if I fed an image, you do convolutions, then you do the spooling operations, you do that several times until you get to the bottom layer, and then you do the transpose convolutions to get back to the same size as you started out with. But the beauty of neural networks is, if that's not it, that's not the only thing that was implemented. They also implemented the skip connections. So in every layer, they fed information from the same level. So they took whatever information was here, concatenated with whatever information you got from propagating through here, and then kept that information as they transpose convoluted as it went. And each of these operations have convolutions that the network will learn when you train it. So the reason you do that is because remember I told you that as you go earlier in the neural network, you have more location information, like you know where the edges are. But deeper in the neural network, you have more high-level information, like where okay, this image has something that looks like a cat's ear or a cat's eye, but you don't have location information. You don't know where that is. But the skip connections allow you to keep that information. So it's saying that I'm using both the location information and the deeper, higher feature information that my neural network learned as it propagated, and I'm keeping both of them to sort of enhance the amount of information I have. So these skip connections are really crucial for the neural networks to work. If I didn't have these, it wouldn't work nearly as well. So I want to do the exact same thing. This is a filtering process, except I don't want to know where a car is, where the road is, where a building is. What I want to know is I want to start with a noisy image, and I want to I want to start with a noisy signal, and I want it to give me a clean signal, right? So that's what I do. So I take the unit, and these are things you can build yourself. They're not too hard. I take the unit, and the information I provided is the noisy image, and the target I provided is the clean signal, the CWT of the clean signal, right? Like this is how it should look like if you had filtered out all the noise. And then I train it for several epochs, and one epoch is when I pass all the data I have through the training once. So I train it for, let's say, 10 epochs. And then my neural network actually learns to filter out the signal. So you might, so this is just saying, so this slide is just telling details of what I use. So in order to compare, so when this neural network spits out a clean image, you need something else to compare it to know. So which is the clean image, right? So, but the neural network will spit out an image, and you want it to compare it to the actual clean image. So you need to define a loss function, and the simplest loss function you can define is the root mean square error, which is subtract the two images, square it, take the square root. That's the root mean square error. So we use that as a loss function, and we repeat the procedure until I see the loss function is no longer decreasing, until I see the validation loss function is no longer decreasing, which means, and that also makes sure that I'm not overfitting. So, okay. I train on 90% of the synthetic data I generated and keep 10% for validation purposes. Now you might wonder how good it works. This is the sort of visual proof. So this method I call noise to clean, because my input is a noisy image and my output is my target was a clean image that I trained on. So it's called noise to clean. And if you look at it, I don't like it's supposed to look like this if there was no noise present. This is a noisy visualization, and this is what the neural network outputted after training. So this is data that it had not seen before. It's in the validation data set. And you know, at first I had to go back and check that I'm not plotting the same image twice because they look very similar. And if you look more closely, there's some minute differences, but it does a really good job of predicting what my signal would have looked like from if I just gave it a, you know, in this, I can maybe, if I squint my eyes, tell like maybe this belongs to gravitational wave signal, but I can't really tell that this is how it's supposed to look like. But the neural network learned to filter out the noise and just keep the clean signal. Now let me give it data from the benchmark data set, which it has definitely never seen because this data I never, you know, I didn't use it in training at all, right? So this is data given to me by a competition. This is Hanford, Livingston, and this is the output. This is what the neural network outputs. This is the signal in Hanford. This is the signal in Livingston, and you know they should look the same because they are the same. Even though the Hanford and Livingston see the same signal, the only difference is one sees it slightly later than the other because it takes gravitational wave time properly. So it learned to, like here, you can't even tell. I can't tell by eye, like maybe this is like part of signal if I squint really hard. But it does a really good job of finding out where the exact, how the signal should look like and where exactly the signal is. So, okay, that's good. So for nice to clean, this method where I use the information of the clean signal, it did a pretty good job to reliably filter out the noise. It generalizes well to the benchmark data set. I don't have the phase information because I threw it away, right? But if I had the phase information, if I found a way to keep the phase information and also clean it through this filtering process, I could inverse CWT transform and then get a time series out of it. So then I would really know how the gravitational wave signal looks like in time series. Yeah, and so what is the purpose of this? So what I would like to see if it can be used for, if you remember, I told you match filtering is extremely expensive. So I want this to be a way to speed up the match filtering because if I'm able to keep the phase information and spit out how the signal should actually look like, I should be able to start out with a good guess of what my merger parameters are. So then I can pull the correct signal from the template bank and do a instead of going through all the 250,000 templates in the template bank, that will narrow down my parameter space by quite a bit. But again, that relies on me keeping the phase information. I think I know how to do that, but I haven't implemented that yet. So by the way, this neural network there's drawbacks. So it's trained only when the signal is present. So even if you gave it complete noise, it will reconstruct some random looking signal. But we have two detectors. We have Hanford and Livingston, and the random looking signal between those two detectors, there's no reason it should look the same. So it will reconstruct some random looking thing in Livingston and some another completely different random looking thing in Hanford. And since there's no coincidence, we say that, okay, that's how we classify that there is no signal present. But if they coincide really well, then that's a good sign that there's a signal present. Okay. Now, what if you didn't have a way, like we didn't know GR, but we somehow built LIGO, and you didn't have a way to predict how the black hole merges look like, right? What if noisy signal is the only thing I have access to? And that happens a lot in real data. So some people figured out that you actually don't need a clean signal to figure out to actually perform this filtering process. You can do it with just completely noisy signals. And you might ask, how is that possible? The explanation is simple. The average of noisy data sets is the average of noisy signals, if the signal is present, is a clean signal. So if I feed it one, but for this I need two snapshots of the same event. But LIGO gives me that, right? So LIGO gives me one snapshot from Hanford and one snapshot from Livingston. The only difference between them is they're slightly time delayed, but because I have this time frequency uncertainty principle thing going on, their chirps match really well with each other. So there's no mismatch in where the chirps are present. So I can just use Hanford as the input and Livingston as the target, and my neural network will learn to latch on to the common parts of the signals between them, and still learn to filter noise from signal. So, so this is called a noise to noise approach. I guess people figured out first for actual images, like if I take photographs, and the photographs have some noise in it. If I take the same photo multiple times, I can just use that for training, and it will eventually eliminate the noise. So this is useful for where it's expensive to take photos, like if I have a telescope, like Hubble telescope or something, and if I get some grainy looking thing. Yeah, sorry.
Signals wouldn't be exactly the same underlying signal because the two facilities are different orientations. So
Right, but remember I'm throwing out the phase information. So as far as this CWT is concerned,
but if it was at exactly the wrong orientation, then one facility wouldn't see any gravitation.
yes, that's right. So it depends on the inclination, and of course, like you can have there is a possibility that only one facility sees it and the other one doesn't. But that happens very rarely, right?
Right, but they still be slightly different. So do you account for that? at all?
No, there's no, I can't account for that if the other one, like, yeah, you're right. So, but yeah, I don't account for it. Like, I don't think, all I tell it is to give me a set of simulated gravitational waves, one for Hanford and one for Winston. So it's, it's definitely true that, so it already offsets them time-wise, depending on what the inclination is. And I'm sure it does also offsets in amplitude, depending on where the source is. But, I actually never encountered a signal which was completely 0 and 1 and present in the other.
Well, yeah, that's an
Right.
extreme example, but
Sorry?
that's an extreme.
That's actually an example. Yeah, so yeah, but yeah, I haven't seen that yet, but maybe in the maybe in, like somewhere in this 500,000 images, maybe there was some example of that. I can't tell by eye, right? I can't even tell if this is an image where signal is present. I can't tell if there's any signal in there or not. But good point. Thanks for. I hadn't thought of that actually. Yeah. So now I don't even need my synthetic data set because I can just take my benchmark data set because I'm using only noisy signals, right, to train my data. Sorry for the typo. My metric is the same, which is the root mean square error. I train because the benchmark data set is labeled. I know which one has signal present, and even though I can't see it, and which one is only noise. I can still figure out. Sorry. What I did was I trained two networks. One only where the signal is present. One only where the noise is present. Actually, the reason for that is because this noise to noise method works when the noise has 0 mean, but in this CWT image, I don't have any zero. The noise is not 0 mean. So I train a neural network only when the signal is present. I train a neural network only when the noise is present. Of course, only when the noise is present, it just learns to map garbage onto garbage. So it just an average of these images basically. And I subtract those two to see if there's a signal remaining when I use it on the next data set. On the data set that it hasn't seen before. So, okay, how well does this work? Works reasonably well. It's not like nice and beautiful and long looking like the noise to clean, but that's expected because I started out with noisy images, so it's not going to perform as well. But it learns to latch on to common things present in both signals. Even though I can't see it by eye, it knows it's there. And it filters it. So this is what the signal would look like in Livingston, and this would how it would look like in Hanford, and they're coincident with each other. So in this case, I'm reasonably confident that this is an actual signal that's present and not something that the network has hallucinated. So that's the noise to noise approach. Now you might ask, why is this useful? Well, you can have alien spacecrafts going, generating gravitational waves with the warp drives, and I don't know what the template of that looks like, right? We don't know how things that we don't know look like, obviously. So, but this method, if you could tell me that there was a signal present, like whatever time series I saw is not consistent with just pure noise. If you could tell me, but I don't know what the nature of the underlying signal is, I could still use this method and it would still latch onto the common signal, and I can still get the common signal out of it, even though I didn't have a template to begin with. And this is great because this will work for cases where I don't have a filter to perform match filtering. So this is, I would say, like, even more so than noise to clean method, even though that performs much better. To discover stuff that we don't know how it looks like, I would say this is a more powerful approach. It's completely, so that's what I was describing, it's completely data driven. And it's ideal for a case where we do not have an access to what a clean signal should look like. Of course, the drawback is it's not as clean looking as our original noise to clean approach, where I knew what the clean signal should look like. Okay, now you're like, okay, this is great. So what? You talked about some competition. Just tell us how you did it. So the competition started out to detect binary presence of gravitational wave signals. And of course, because of all the noise present, any method you use, even something as good as match filtering, it's not going to be absolutely perfect. So it's going to give you some distribution of noise only signals. This is like the SNR, signal to noise ratio on the x-axis, and some distribution where the signal is present. And if I wanted 100% accuracy, I don't want any false positives, I would like cut it off here, saying everything about this SNR is what I'm considering my signal to be present. But that's not really good, because I'm throwing out a bunch of things that were a signal, just because I'm afraid of getting a false positive. So what's the best metric to use in these cases? And it's called the receiver operator characteristic, which or the ROC curve. And it says that as I vary the threshold of my signal to noise ratio, quote unquote, as I vary the threshold of my signal to noise ratio, how does my true positive rate go with the false positive rate? Because if I start out here, my true positive rate is 1. I don't have any false positives. But if I keep moving in that direction, at some point I'm going to, at some point I'm going to start having false positives as well. So it's going to trace out some kind of curve in this parameter space. And the ideal is 1. So if my curve went like this and like that, then that's the best I can do. But anything in between is a measure of what my confusion is between what signals are do actually have a gravitational wave and what signals don't. So the area under the curve of this ROC curve is the metric we use to see how well we perform, and that's the metric that the competition used. That's why I chose it. So before I don't know how, okay, 15 minutes. Okay. So before we move on, I'd like to tell you what people in the competition did. This is not the best method to do it, but this comes very close to the best method, and it's one I can implement easily. So this is what I chose to benchmark against. So you guys may or may not have heard of it, but there's very deep image learning models called EfficientNet, like 60 million parameters. It's 60 million parameter convolution neural network, and it's trained on like all images on the internet. So if I want like various classification, whether it's just in animals, whether it's an ant or a hen or a bee or something, the network has already been pre-trained to identify it, and I can actually download the weights along with the network. But yeah.
So just for comparison, how many parameters is your search use?
Yeah, I don't know, like if you ask, like, I mean, I think of a ant and a hen as two separate things, obviously. So, but I don't know how to think of the latent space in my model, but obviously much lower than what this network is trained on. So the beautiful thing of this is that I can just take this network, I can unfreeze the number of layers I want to unfreeze, keeping the rest of them frozen to what it learned, and I can retrain it for my own purposes. So if you have, like, it will be an overkill, but if you wanted to classify cats versus dogs, you could download this network yourself. It probably already does that pretty well, but if you wanted just to focus on that, you could unfreeze all these layers, keep the architecture, retrain on all the layers, and you will get your own cat versus dog classifier. And this is called transfer learning. But I can just use this to see whether there's a gravitational wave present in the signal or not. So inherently, this, not in the way a human will understand, but what this EfficientNet is doing is sort of filtering the image, but not in the way you or I would understand, right? It's just somehow latching on to the presence of the signal. Okay, and then I train. So I take the EfficientNet. I choose two options. One where I only unfreeze the first layer, and one where I'm using the entire neural net to retrain again, just to see how it performs. And then I compare it to my method, which I filter the image first. So, okay, let me describe you. So my baseline is I take the time series signal, I whiten it, I convert it into an image, I feed it to the trained efficient net, and then it spits out true or false, right? The other method is I take the signal, whiten, I CW transform, then I clean it, I filter it through the neural network I developed. The idea being that it should perform better if it's already given a somewhat clean signal to work with, right? So then my neural network outputs another image, which I then feed to the efficient net, and then I classify it as true or false. So how well does this work? It doesn't work as well. So I first didn't know. Okay, so if I only keep the last layer of the efficient net, I destroy it. I can easily destroy it, and the reason is because I only get the last layer, right? So if I look at the AUC scores, then I'll get my AUC to be 0.73 if I only retrain on the last layer of the efficient net. But if I use my UNet noise to clean to pre-process the images before I fed them to the efficient net, then I perform extremely well because all the heavy lifting is already being done by the filter I trained to clean it up. So that's good, but that's not what I really want to compare. What if I kept what if I retained the entire efficient net? So then it does really well. It gets an AUC of about 0.83. Unfortunately, I don't beat it, which is bad because I'm using 2 networks instead of 1. So in theory, I should be doing better. But there seems to be some fundamental limit I'm bumping up against. And my AUC is not as good. It comes close, but it's not as good. And for noise to noise, it's not a huge difference. Some might argue that's just within the standard deviation, but this is being done on 150,000 signals, so the standard deviation is not that much. This is really performing my method is really performing slightly worse than what people in the competition did, which is just to use the efficient net in the first place. The noise to noise performs even slightly lower compared to, which is expected because it's trained on only noisy data. So we can ask what's going on. Why is it not performing well? And this is something called a confusion matrix, which all it's doing is saying, so this is false. Sorry, this is true negatives. So false positives, true positives, and false negatives. And they should all add up to 1. And if I was perfect, I would just have, because half of my things have a signal and half node. If I was perfect, the off diagonals would be 0, and I would just have 0.5 and 0.5 on the diagonals, right? So this is just for, if I just use this efficient net to do it, then this is the confusion matrix I get. But if I use my method, which is I pre-filter it with this noise to clean UNet before feeding it to the efficient net, then you see that in some cases it does better. So I'm doing better on the true positives, but I'm also getting more false positives, and that's sort of penalizing my receiver, the area under the curve metric that I'm using for. But you would say if having false positive is not very important to you, then sure, this is just slightly better. But it's not meaningful because it's not extracting more information out of it. But it comes close though. Okay. So, all right. So I would say the noise to clean UNet comes closest to the benchmark that other people in the competition were considering. Noise to noise performs a bit worse. And so one might ask why did pre-filtering the signal using the noise to clean UNet not give me any gains? And the reason is that the noise to clean filter is trained only on positive samples. So sometimes it's hallucinating. In all the cases, it's hallucinating a signal, but very rarely it's also hallucinating a signal coincident in both Livingston and Hanford. So that's why it's showing up as a real signal. But in reality, the signal is not there. It just thinks it's there. The other reason might be I trained the noise to clean filter on synthetic data that I generated, which does not necessarily map on very well onto the real data or the benchmark data that I was considering. Of course, if I have more detectors, it's hard to have hallucinated signal in 3 detectors or 4 detectors or 5 detectors. So it will hallucinate or it will fake hallucinated signals less when I consider more detectors. Yeah, and I think if I'll perform, I believe I'll perform better if I also keep the phase information which I threw out in the beginning. Okay, so in conclusion, so this is something I want to emphasize. So the problem was to detect the presence or absence of gravitational waves. It was not to filter the signal. When I'm filtering the signal, I'm doing something extra. It's not performing as good on the final task, but that doesn't mean the tangential task I performed of pre-filtering the signal is not inherently useful in itself. So this noise filtering method, just to summarize again, relied on filtering noise by training on noisy data and the clean data. But my noise to noise method was completely data driven. So in principle, not just for LIGO, in principle, if I have a data set which is noisy and I don't know have any template to compare to of how the clean template should look like, then I can use this noise to noise method to kind of extract the signal out, because this noise to noise unit will still latch onto the common signal present in. But the thing about this is I need to detect 2 detectors. I can't just do it with one. Yeah, and in LIGO, this is something I want to think more about. So this is more future work. Okay, forget about signals. Most of the time in LIGO, 99% of the time, I'm just 99.9%, I'm just observing noise. So, but the neural network doesn't care what is signal and what is noise. It's still going to latch on to the common thing between the 2 signals, right? So can I actually use it to identify sources of noise and then somehow find a way to subtract them? But yeah, I'm not sure. That's one application of it. Yeah, and in conclusion, the filtering ultimately didn't help improve the probability of detection of the binary presence of gravitational waves or not. But I think what it can do is it can give a good. I'll do this once I can reliably keep the phase information in. But what it can do is give a first initial good guess of what the binary black hole parameters are, narrowing my search for my match filtering technique, and then this can help speed up the match filtering technique process. And finally, yeah, I think I said most of this already. This is just like a couple of ideas where it might be useful. Happy Leap Day. Thank you. Yeah.
So, I don't know, maybe I'm a little confused here. So at some point you mentioned that so even if like the signal was you train your machine with the signal, right? So with gravitational wave.
You mean the clean signal?
Yeah, with the signal. Yeah. So then even if you inject like a noisy the signal, so it gives something.
Yeah, even if I inject pure noise, it will like try to reshape that pure noise into something like this, because that's what it's trained, right? It doesn't know, but it will look weird. It won't look like a nice thing like that. But plus, in addition to that, I'm giving Hanford and Livingston, and they will not look the same as each other. So the coincidence between them will not be one on one.
But then even the gravitational wave signal comes with some noisy part as well. Or just
You mean even the clean gravitational
Yeah.
signal? What is noisy part?
So the clean means just really noise is completely removed.
Yes, it's completely. Yeah. Because I mean that's how my first unit worked. I trained it to filter out the noise, so I really needed to know how the clean signal looked, totally clean signal looked.
Okay, so then the noise to noise.
Noise to noise didn't need it. It just needed 2 photographs of the same event. Yeah.
Yes.
So can it also be used for like this nanograph?
Yeah, and so I asked some nanograph people. they were slightly skeptical, but I managed to convince them. So I am running some like toy models for them. So in nanograph, the idea is if you have two radio telescopes looking at the same pulsar. So what they were excited about is not what I was excited about. I was excited about improving timing for pulsars. But what they said they would be excited about is if you have two things looking into the void, if it was just one thing, then it's completely dominated by noise, right? Because you don't know the pulse shape inherently. But if you have two of them, then even though it's completely dominated by noise, I can use this method to look at really faint pulsars, which would not have if I have two radio telescopes that are whose noise there's no correlation, who are well separated enough that their noises are not correlated with each other. Yeah, they were saying that because they don't know, if they knew the template of that very faint pulsar, which is not possible because they haven't looked at they don't know it exists yet, then they would just do the match filtering and get, that would be the end of that. But since they don't know what the pulse shape look like, it's really good if two radio telescopes are staring in the same direction, and this method can be used to detect then very faint pulsars.
Yeah, so I guess, that here, probably you briefly mentioned, but basically you train your machine with the left-quarter merger data.
Yeah, I mean, yeah, that's just, there's a LIGO library which just spits out how the clean waveform should look like.
But what if you, the test, with like a gravitational wave signal, but not from, left-quarter mergers, but something else? Maybe, I don't know.
Yeah, then the noise to noise will be useful because then I don't have a template, so I can't do match filtering. But one thing you'll need to tell me is that these are the times, this is the set of time series which don't agree with noise only, but we don't know what the signal looks like. But then you can use noise to noise to extract out what the signal looks like.
So then your machine can say, okay, this, this is likely to be something.
Yeah, that's right. Yeah.
Has this method been applied to LHC data? You can apply it there.
How? If you have idea,
So for example.
I'm a man with a hammer. I need.
Yeah,
nails.
actually, I can see that.
Yeah.
So for example, quad jet versus various kinds of gluon jet. The origin of jet. If people apply various neural network techniques to.
But what needs to be filtered in that? I don't know. I don't know much about LHC. So
So you train it on some known quad jet. And
Okay.
then you look for this data which just look, jets from various or origin.
yeah.
And then you try to figure out whether it's really, it has found the gluon jet or versus.
So you want to tag it.
Right.
But tag, I can just develop a neural network where just like the cat versus dog, I can train the neural network to say whether it's, quad jet versus gluon jet. The special thing about UNet is it comes back to the same input space as you started out with. I fed it an image and the output was also an image. The output was not a label. So what you're saying, yes, you can make a neural network for it, but it won't be this one. Because this one starts from an image and comes back to an image. Whereas that one you're saying, it starts from some data, maybe you can write as an image, and then it outputs a label, which is whether it's a quad jet or gluon.
But it gives us somehow the filter of the noise.
It filters out the noise. So if you have noise, if you have things that you want to filter out noise for, let me know.
And actually, let's data, but not only the jet images, but also the pilot. So it's a pure noise.
Oh, really? Okay.
Yes, the noise, some noise part. I mean, the noise is basic sort of the background, like a pilot data.
Yeah.
And on top of that, you have a time like a jets.
I see.
The one you just said, the probably just said, they're looking. I mean, in principle, they look different.
Yeah.
But in the presence of the pilot,
Yeah.
sometimes you get confused.
Right.
And then your the machine.
Yeah.
And the potentially filter out the pilot part. I mean, so they remove the pilot using some kinematic method.
Oh, I see. But you're saying this thing can learn to filter out the pilots.
Right.
Okay. Yeah. But
Then
maybe I
if some image, like a
Yeah.
pure alone the jet image and plotted image. And
Yeah.
it's better to
Maybe.
distinguish.
Yeah, maybe I can talk to you more. Oh, well, I've thought of uses for it, and people here are more experts on this than I am in terms of, so I thought like the liquid argon time projection chambers, right?
So
There's some spread in that, right? Like when something passes through. But if I have access to a clean, like simulated clean signal where I know how things look like, then I can probably figure out a way to how to reduce that spread and then do a better job of, I don't know, but I've thought about it, but yeah, not in any great detail. Uh, All right, thank you.